All right, so now we're going to look at the Newton method for root finding. Okay, so let's suppose we're given a function which is twice differentiable on the closed interval from a to b, and f of alpha is equal to 0 for some alpha which is in the open interval from a to b. Okay, so what I'm going to do basically is that I'm going to do a Taylor expansion of the function about the root of this function. Okay, so I'm going to consider a Taylor expansion about x equals to, sorry, not about x equals to alpha, but x equals to some unknown, let's say. Okay, about x, that's it. Okay, but I'm going to do a Taylor expansion of the function value at the root. Okay, so f of alpha. So by definition, then f of alpha is 0. Okay, but we also have a Taylor expansion about the point x. So that's f of x plus f prime of x alpha minus x plus a remainder term from the Taylor remainder term. So this is 1/2 f double prime at some unknown point c, then alpha minus x squared. Right, so this is the linear expansion. And then this is the remainder. Okay, so let's think about what is really happening here. What's really happening is that you have some function. Let's say that is x. Okay, and then what I've done here with the linear expansion is to replace that function by its tangent line, basically. Okay, and what we're going to do is that we're going to assume that if x is close to alpha, then what happens is that this alpha minus x term is small, and in particular alpha minus x squared is very small. Okay, it's very small. So as you might expect, I'm going to drop it. Okay, so we omit the remainder term. All right, and then this is saying that 0 is approximately equal to f of x plus f prime of x alpha minus x. And so you can solve for alpha, all right, from this equation. So alpha is approximately equal to x minus f of x over f prime at x. Okay, so what is this approximation to alpha? Where are we getting it from? So as I said before, what happens when you do this Taylor expansion and you omit the remainder term is that you replace the polynomial, well, you replace the function f of x by its linear polynomial approximation, so this tangent line here. And then, and I'm looking essentially for the root of this tangent line. So I'm going to extend this all the way down. It's like until it touches the x-axis. And this is the candidate alpha, so to speak, which I get when I evaluate that right-hand side. Okay, so alpha is approximately that. And again, if you're sort of close to the root, then this is not too bad an approximation. So so this is obviously not exactly equal. The root is not exactly equal to this, and that's because this remainder term is in general not 0. Okay. All right, but in any case, it's like you can imagine using this kind of approximation successively to construct a sequence of approximations to the root. Okay, so let me give you the definition then of the Newton method. So the definition is as follows. right? Newton's method is an iterative method based on the iteration alpha n plus 1 is equal to alpha n minus f of alpha n over f prime of alpha n. So what's basically happening is that the x here is the previous guess to the root. You approximate the function at that point by its tangent at that point. You approximate the function by the tangent at that point. You look at the root of the tangent line, and that's your new iterate for your guess as to what the root is. Okay, and you just repeatedly apply this. So this is what is known as the Newton method, or Newton's method. So we can generate sequences, a sequence of iterates, alpha 1, alpha 2, and so on, from some initial guess, alpha 0, and alpha 0 is your initial guess, right? All right. So let's look at an example of this. I should mention that Newton's method is an example of this paradigm for constructing numerical algorithms, which I had alluded to earlier, which is that you take the function, you approximate it by something, and you try to find the exact solution of the approximation, right? So you were trying to find the root of a function f, you replaced it by this linear interpolant, you find the exact root of that linear interpolant, and that's your new guess, and you can keep doing this, right? So many methods you'll see is based on this idea, what we'll see later on in the class is how to systematically construct these kind of approximations, not just with the Taylor method, but with what is known as an interpolating polynomial, where the data is provided to you not just at a single point, but at a bunch of different points. Okay, anyhow, let me try to illustrate this Newton's method with an example. So let's say you have f of x, which is x cubed minus x squared minus 3x minus 3, which was the example we saw before with bisection. And you know that this has a root in the interval from 0 to 2 because the function changes sign from 0 to 2. Okay, and so in order to apply Newton's method, I have to compute its derivative, the derivative of the function I'm trying to find the root of, right? So that's 3x squared plus 2x minus 3. Okay, so let's start off my initial guess with, say, the right endpoint. Alpha 0 is equal to 2. Then you can check that alpha 1 is equal to 2 minus f2 over f prime at 2. That's 1.76923 with a bunch of other digits. And then alpha 2 is equal to alpha 1 minus f alpha 1 over f prime alpha 1. And this becomes 1.73292 with a bunch of digits. So after just 2 iterations, right, the difference between alpha 2 and the actual root, which is you can check one of the roots is the square root of 3, which is the root in this interval, right, is about 8.73 times 10 to the minus 4. So you really get very, very good accuracy after a small number of iterations. So this is meant to illustrate one of the advantages of Newton's method, which is that when it converges very fast. Okay. All right. So let's look at another example. So with the same function, so now let alpha 0 is equal to 0, which is the right endpoint. So you can check that alpha 1 is equal to 0 minus f at 0 divided by f prime at 0. This gives you minus 1. And alpha 2 is equal to minus 1 minus f minus 1 over f prime at minus 1, which is also minus 1. So it turns out that minus 1 is also a root. So alpha equals to minus 1 is also a root, but not in the interval from 0 to 2. Okay, so one of the sort of challenges, if you will, it's like with Newton's method, is that there's a sensitive dependence on which root you end up in if there happens to be multiple roots. There's a sensitive dependence on the initialization that's like you started with. So depending what alpha 0 is, you could end up with different roots, as this illustrates, and it's not always so clear which root you'll end up in. So I should remark that there are some very beautiful fractals you can get, which are called Newton fractals. So fractals are basically geometric structures which have infinite detail, for lack of a better term, which is to say that as you zoom in closer and closer to it, there will be places where there's more and more sort of detail in it. It doesn't sort of become straight lines or anything to that effect. So they're what are known as Newton fractals, and they come from applying Newton's method to polynomials on the complex plane. So because of course when you look at a polynomial, in general the roots of a polynomial are complex and they're not necessarily just real valued. And if you have multiple roots, if you have particularly if you have say 3 roots or more, and you apply Newton's method to it, you can basically color the complex plane by starting at a point in the complex plane, and depending on which root Newton's method eventually converges to, you could color it one of n colors, where n is the number of roots, and you'll find that those things have very, very sort of complicated, sort of very detailed structure, which it's like which persists irrespective of how close you zoom into it. So that's something worth looking at. So what are called Newton fractals, and you can find that it's like on the internet. All right. Anyhow, so let me make a few remarks about Newton's method. So the first of which is that you oftentimes get rapid convergence. So usually. And then what we'll see in a little bit is under what circumstances you're guaranteed to converge to a root. So more or less what has to happen is that your guess has to be close enough to the root in order for it to be in order for Newton's method to be guaranteed, it's like to converge to that root. Okay. All right. So the second thing is that Newton's method may not converge. And there's a strong dependence on the initial guess. And again, you can see this strong dependence in initial guess. It's like by searching Newton fractals. As to the part about not converging, let me sort of try to draw for you an example of a function. It's like for which Newton's method may not converge, or actually does not converge, at least for certain choices of initial points. Okay, so here, imagine you have a function which is like this, and then we start off with alpha 0 like this. So as we talked about, Newton's method takes the tangent approximation of the function at the initial point, looks at the root of this, and then that becomes my new iterate. Right? So you can imagine a situation where something like this happens, where in essence what happens is that you start with alpha 0, right? You get the tangent line to that, you get alpha 1, and then the tangent line to alpha 1 gives you back alpha 0. And so this is an example of a situation where Newton's method would not converge because the iterates would keep alternating between alpha 0 and alpha 1. Right? It will sort of keep going back and forth. It would never converge to the root, which is at x equals to 0. All right. So yeah. So anyway, so that's you know, a illustration of a function where the Newton's method is not guaranteed to converge. Actually, does not converge. Okay. So the third one is that you need information about the derivative, right? So f prime is needed. Okay, so let me state a theorem for now about this issue of convergence. Right, so let's say we have f and it's twice differentiable in the interval from a to b with some root alpha, which is in this open interval, and yeah, and f at alpha is 0. Right, so you furthermore suppose that the derivative, it's like at the root, is not 0. Okay, then the claim is that there exists some delta greater than 0 such that for all epsilon 0 in the interval sort of with delta about alpha, so alpha minus delta, alpha plus delta, the sequence alpha n generated by Newton's method converges to alpha. Okay. Okay, so basically what this is saying is that if you have a root and it so happens that that root has a non-zero derivative, okay, or the function has non-zero derivative at the root, right, then there's some you know, neighborhood, non-vanishing neighborhood around the root where if you start Newton's method with an initial condition in that interval, then the sequence of iterates you get from Newton's method will converge to the root in question. Okay, so let me, and we won't prove this for now, but we'll prove this later in the context of what are called fixed point iterations. So it's going to turn out that Newton's method is an example of a fixed point iteration, and then there's a general result about convergence of fixed point iterations, which we can then apply to establish that Newton's method does converge for suitable choices of initial conditions or initial guesses. Okay, so let me make a few more remarks before we finish. So the first of which is that you still get convergence even when f prime at alpha is equal to 0, but it is much slower. Okay, and the second of which is that this sort of interval, it's like about alpha, could be very small, delta may be very small. So we need oftentimes a good starting value. Okay, so this is in contrast to bisection or false position. where you only need to bracket the root. Okay, so that's something to be aware of. All right, so let me just stop here for now. And second, the next thing we're going to talk about is the secant method, which is a slight variation of the Newton method, where you avoid the need for sort of computing the derivative, it's like, of the function. All right, so let me just stop here for now.